Alright, now we'll talk about life in the universe. Context of life, astrobiology, searching for life beyond Earth, and SETI, the search for extraterrestrial intelligence. So, we try to understand how life evolves on Earth and the processes and constraints required to allow life to thrive, and then contextualize that in the rest of the solar system and universe. This is the science of astrobiology, which is what does it take for life to exist, what are the conditions for it, and where do we find those conditions in the universe. So the main thing about life on Earth is that we are what are called carbon-based life forms, and carbon-based life forms are use carbon because carbon can be grouped together in long chains to create the wide variety of chemical compounds needed for chemistry that we use on Earth. The concept of the Copernican principle is that there is no special place in the universe. So the Copernican principle is that our solar system is just one of hundreds of billions. We are not in a special spot in terms of there's nothing unique about our location that would make life unique to Earth or our sun. So this could mean that there could be plenty of life out there around other stars. There's billions of stars in our galaxies old enough for life to have developed on a planet around them. It's possible Mars and other planets and moons in our solar system either currently have life or had life. What we want to know is whether or not organic biochemistry is likely or unlikely in the universe. Are we just an exceedingly rare outcome, or is organic biochemistry a regular part of the chemical evolution of the cosmos? We don't know the answer, but we're looking for it all the time, and we're actually getting closer to getting the answer to that question. So then the question is, if the Copernican principle is applied to us, then there must be intelligent life all over. It should be common to us. We are not special, we are normal. Therefore, it should be probable and common that life, advanced life, intelligent life, is quite out there, quite present. And this is the Fermi paradox that Enrico Fermi posited and said, all right, if the Copernican principle is true, where is all the intelligent life? If the universe has this tremendous capacity for advanced civilizations, then where are they all? There are a bunch of solutions to the Fermi paradox. Again, the Fermi paradox is, if life is so easy and common, then why is it so rare? Why don't we see evidence for life everywhere? There's a bunch of stuff, right? Perhaps we are just one of the first to come online, and we're waiting for to hear from all the other life forms. Maybe they're all just developing at about the same time as we are. Maybe, as you may know, by the year 2100, Earth will become uninhabitable because of climate change. So maybe we just, every civilization advances to a point where they cause themselves to go extinct. Maybe asteroids or other things prevent a civilization from advancing far enough, and we have just survived long enough so far to get beyond most of the other civilizations. Maybe something is out there that doesn't want us to know about it, but that seems pretty unlikely. So astrobiology is the study of the origin of the chemicals in the universe, how they are distributed around the universe, what are the conditions for what we call a habitable environment, and how has life on Earth adapted to conditions that we might think of as extreme. So the main thing we need are these amino acids and organic compounds, and these two things together make up the proteins, and the proteins do all the stuff and carry out all the work of the cell. We see organic molecules in the clouds of gas and dust beyond Earth. We see them out in space, so the chemicals that are responsible for chemistry on Earth and life on Earth is pretty regularly accessible in the stuff of the stars. So one of the more famous experiments is the Miller-Urey experiment, where they just took some of the initial chemicals thought to be on the early Earth, and they shocked it with like lightning, and they produced even more things, and that was one of the early experiments to show that it's possible using natural processes to create all of the chemistry necessary for life on Earth. The simplest cells contain millions of molecular units. This DNA and RNA, deoxyribonucleic acid and ribonucleic acid, these molecules that contain all of the information that our life forms have, are responsible for all the information passed on between cells and biological systems. They contain the instructions for how a cell is supposed to behave. The chicken and the egg problem is referring to the DNA and the RNA working together. So which one came first? The RNA is generally considered to be the early precursor to DNA in the earliest life forms. And so life became more and more complex over time, and that is another example of that. So some of the earliest life forms show up in these things called stromatolites, and they are basically these bacteria. They want to see the sun, but they produce this calcium layer as a byproduct of absorbing light from the sun, and so they actually build up and out, and they end up building these little piles of rock. And so we have evidence from these things by old fossil stromatolites from 3.4 billion years ago that there was bacteria that was using photosynthesis to power their functions. And the photosynthesis, the byproduct of photosynthesis, is oxygen. And so the presence of oxygen on the Earth comes from primarily the bacterial activity at the early, a billion years after the formation of the Earth. So that again gives really clear support to the idea that life should be pretty common if it formed as early as a billion years after the formation of the Earth, or sooner. Then that's a pretty amazing fact. So a habitable environment is one where the environment is capable of hosting life. So generally we think of anything that has liquid water on it as being habitable. If it has liquid water, it's probably in the habitable zone. And the habitable zone is an area around a star where the temperature is such that the planet has liquid water. Another example are around the moons of Jupiter or Saturn. The gravitational frictional heating, called tidal heating, between the moons and the planets might keep the moons and planets warm enough to have liquid water. For sure, Europa has a liquid water ocean. So we think NASA wants to send a submersible probe over there to swim around in the ocean and look for life there. So this is a big deal. Let's see, continuing on. So, yeah. So the main requirements for life are water and then carbon. And all carbon-based life forms use the carbon atom as their main hub for producing all their chemistry. So there's certain elements of life called extremophiles, and extremophiles are bacterial or other forms of life that live in extreme conditions. That would be at hot springs, very acidic springs in Yellowstone, for example, or at the bottom of the oceans, what we call hydrothermal vents, or in Antarctica in the ice. So no matter where there's a river of acid, Rio Tinto. The Anyway, the point is that we find life in all of these places. So it seems like no matter what the conditions, life finds a way, to quote Jeff Goldblum, no matter what sorts of extreme conditions there are. So that's crazy. Blah, 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 blah. But there's some areas on Earth where we don't find life. So in order to find life beyond Earth, we look for biomarkers. That could be in the form of some crazy signal coming from another planet that would be artificial. It could be in the form of looking at the atmosphere and looking at the spectrum of light that's comes from it to determine whether or not it has oxygen in the atmosphere, or methane, or some other signs that there might be life on the surface of the planet. So we're looking for that. Life on Mars, we know for sure that Mars was very wet for a long time, and there were oceans on them. And there were oceans on Mars as long enough for life to form, or at least as long as life formed on Earth. So the thought that Mars should have had some life on it is a pretty compelling argument. We haven't found any evidence of them so far, but it's still possible that there is evidence from long ago of bacterial life, or maybe early life forms, or some sort of life, or some evidence of the precursors of life. And it would be very important if we find that on Mars. If we don't, then that also tells us that maybe life is a lot rarer than we think it should be, and maybe Earth is even more special. Okay, so in the outer solar system, around Jupiter's moons, Saturn's moons, there's this thing called tidal heating that allows the planets to the moons to stay warm, because they're being stretched and pulled and twisted and turned by Jupiter's gravity, and that causes frictional heating, where the moon is literally rubbing its inner parts together, creating enough heat to maintain a surface temperature which is warm enough to create liquid water. And so there are some moons that have liquid water, and some of these moons have a high probability that maybe they have life, and it would be very wonderful to go check that out and take a look. This is Europa. This is a planet with a surface of ice, and underneath it is a ocean of water, and it would be very interesting to see those things. Enceladus here, Saturn's moon, you can see geysers of water spraying into space. So again, we see the evidence that there's the requirements of life there. The question is, does life actually evolve on those planets? Very interesting. Titan, another image of Titan here. This is methane oceans, methane lakes. They have a water cycle on methane, just like Earth does, where the clouds are evaporated hydrocarbons, and it rains oil, methane. It doesn't rain oil, but liquid methane. It's really crazy. So, who knows what kind of things are on there. We've had a lander on there. It'd be nice to take a closer look at what's going on there to see if maybe there's some other life forms. So habitable planets orbiting other stars. What we look for is the habitable zone. Again, it's a planet that is the distance from the sun, not too close, not too far, but just right to have liquid water on the surface. And that's a complex equation. It has to do with the amount of sun that the planet gets, the amount of atmosphere the planet has. For example, we are further away from the sun than Venus, but Venus is 700 degrees on its surface, maybe even 900 degrees on its surface, because of its very thick atmosphere. So Venus is just on the edge of the sun's habitable zone, but the planet itself is uninhabitable because of its extreme temperatures, because of its the water boils on the surface of Venus. So even though it's within the habitable zone of the sun, or at least right on the edge of it, its extreme atmosphere prevents it from doing that, or allowing it to be hospitable, even though it's within the, quote, habitable zone. This is really cool. This is Earth seen from Voyager. The pale blue dot, Carl Sagan poem inspired by that image. This is the spectrum of light transmitted through Earth's atmosphere. So visible light makes it all the way to the ground, but the infrared wavelengths and a bunch of other wavelengths are absorbed by the atmosphere, which is very interesting. So that tells you also, why you see the colors you see. We see visible light because that's the light that makes it through the atmosphere, through water, through all these, we grew up on a wet planet, so those would be the ideal eyeball wavelengths for us to evolve with. And then the search for extraterrestrial intelligence. Interstellar travel is not a very plausible thing because of the radiation that you'd be exposed to, because of the energy required to get to the speeds necessary to even travel to the closest stars. It's just not possible, and there aren't really any the idea that we could figure out a way to hack the universe on such a level to create interstellar travel is really not plausible, again because of all these other issues that crop up. So there's no aliens that have visited Earth. We can safely say that. We have sent 4 spacecraft out, the 2 Pioneer probes and the 2 Voyager crafts, as well as New Horizons. They are all outside on their way to leave the solar system and end up who knows where. The galaxy is so vast and so empty that the odds of any of these probes actually hitting something is almost zero. They will likely just continue on forever, never hitting anything, even going through our galaxy. But each of them contain a plaque. For example, this one, these are the locations of stars, and we are this location relative to them. So if an alien finds this, they know exactly where our planet is, where our sun is, our soul is. And then we've got this that tells us we're the 3rd planet from the sun. So whether or not that's a good idea is you could argue about. But maybe it would be cool to be killed by aliens. I don't know. So SETI is another thing looking for signals coming from the sky. We're listening with stars. We've been sending signals to stars just to see if anybody will hear us and send things back. So we're looking for stuff. There's all these telescope arrays trying to send signals out or listen to signals. SETI is the search for extraterrestrial life. We're using machine learning and all these things to try to pick through the signals coming from space and look for anything artificial. So far, no luck. So the Drake equation here, this is pretty cool. The Drake equation just tries to estimate the number of advanced life forms there must be out there. And the point of this, which leads to the Fermi paradox, is that even when you put in ridiculously low odds for every chance for the right planet to form, the right star to form, the number of this and the number of planets that eventually can support life, even when you put all that together and multiply everything out, you get, when you have 400 billion stars, you get that there should be definitely more than one planet with advanced life on it like us. So that's another problem that we have to solve. So there's at least, even with the worst assumptions, that you get 100 advanced civilizations even in our own galaxy, which is not a lot out of 400 billion stars. But if it's only one, that's pretty crazy. And then, yeah, so there's some conclusions here that you can read about. Yeah, here's all your things. So in summary, the Fermi paradox asks why, if the Copernican principle is correct, which says there's nothing special about our place in the universe, which says that if life could develop on Earth, it should develop in other places as well. The Fermi paradox says, all right, where is it? Where is all this life? Why don't we see any evidence of any extrasolar life, or extra Earth life? Astrobiology is the study of the chemistry of life out in space, and we find that the chemicals necessary for life are abundant in space, and we can produce them in abundance on something like the Earth. Searching for life beyond Earth, Mars seems like a good candidate for at least some simple life forms to have formed early in its history. That would take a while to pick through. Titan is an interesting world around Saturn. Enceladus and Europa have water oceans that could have a lot of really nice life forms that are living in the oceans. We'd have to take a look with a probe in the next few years. Then there's something called SETI, the Search for Extraterrestrial Intelligence. We are sending signals out to stars. We are listening for signals from stars, trying to look for any artificial signals at all from anywhere. So far, we have not seen anything, and that, again, leads us to the Fermi paradox. All right, talk to you guys later.